Okay, so we're getting recorded. So we're going to talk about, this is from the book, the Stanford textbook, Boyd and Vanderbilt. The book is called, you can download the entire book if you want. Here it is. Let me show it to you. By the way, you can also, there's a lot of textbooks that are online. A lot of universities put all of their textbooks online. And this is a really nice book. It's in the lecture notes. It's also in your syllabus. Again, it has, let's go over the book quickly because I'm trying to get you ready for your project. Notice that their focus is, they call this theory, but essentially the book is on convex analysis. There is a strong focus on convex sets. That's what we're going to talk about a little bit because we did not do that very well. Convex functions and convex optimization problems, right? So notice that, I mean, all the way until here, they consider that to be theory. Nothing about trust region, nothing about line search until later. They have wonderful applications. And if you were to find, including list node problems, regularized, all of those are wonderful. I tested them out. I guess I made a decision not to cover them because every single one of you will be interested in one subsection of that. And, you know, you can tell me if I made a mistake, but okay. Plus, you cannot cover everything. So, and notice that they don't hit the algorithms until 9, which is basically the opposite of what we did. We start with the algorithms, okay? And they talk about it. Notice that there is no line search and trust region. So it's a more traditional display. In fact, they're concerned, the whole book is about making things convex, more or less. Okay, so it's a little bit, it's exactly the opposite. It's kind of very different from our approach, which is give you the state of the art in algorithms and expect you to come up with the problems, okay? All right, but again, you should be able to find a lot of things that we cover. So I admire it for its applications, if you are to find yours. Okay, so the greatest treatment in the textbook is about convex sets, and that's really where it shines. So there are some definitions that we're going to go over. Again, you can download the textbook. There is a link in your syllabus. And we want to cover some of the basic definitions before we go into a really basic concept called multi-objective optimization. Okay? So let's go. All right, so simple definitions. Okay, so we have a line through 2 points, x1 and x2, and basically, notice how they generate the equation of the line using x equals theta times x1 plus 1 minus theta x2. You plug in theta equals 0, you get x2. You plug in theta equals 1, you get x1, and therefore it's a linear relationship that goes between those 2 points. Okay? They have some definitions. An affine set contains a line through any 2 distinct points in the set. That's pretty straightforward. And this is how you define, how you generate that in this case. Solution of a set of linear equations of x equals a, x equals b. Conversely, every affine set can be expressed as a solution set of system of linear equations. Okay. All right. I'm not going to go over their math, and I'm not going to question their math because they are not mathematicians. Okay. So don't ask me to do that. Go after whether they're talking about soups. Did they really get the right definition? I don't care. I'm not going to do it because that's not what their strength is. Okay, they're engineers. Okay, so, all right, so here is an example of a convex set. We talked about this briefly. This is a review. The biggest definition about a convex set is that you put a line through them, any 2 points, you remain in the set. So in this case, obviously, this is not a convex set, okay? Notice that this one has problems too because it doesn't capture its boundary. All right. Convex combination. This is cool because linear programming is going to go there. We'll get it. Where you basically try to get The total sum adds up to 1, so there is a normalization parameter. They are all above 0, and you are summing them up, and that's a convex combination of your points. The convex hull, which is excellent, there is a software that if you have a collection of, notice, okay, let's go over this so you understand. The input are all the dots. The input is all the dots. You give the dots to a software, and it comes back with a collection of lines, right? Line segments that connect the outer points. That's the convex hull. Okay, and this is well, wonderful algorithms exist. We're not going to go over it. Yes.
It's a good way of finding your constraints and equations.
If your points represent, yeah, I guess the points have to be, they're going to be in the interior.
Yeah.
Yeah, if you have to have a convex hull, I'm not going. I have to see the problem. I won't be able to say it. But yeah, definitely you can convexify sets, and once you have a convex set, you get a lot of wonderful results, right? The concept of a conic combination. Notice that here are cones. I need those. They're coming up. Notice that basically you have two vectors, one along x1, one along x2, right? But you're only allowing positive coefficients in front of both directions. And as a result, you can only generate points that belong. It's not a rectangle, it's not a triangle, it goes to infinity, but it's bounded by those two lines. Okay? It's a plane. These are points on the plane. In fact, when you learn about three-dimensional planes, one of the ways to define planes is to give two directions on the plane. Okay? All right. So a convex cone, and this is coming up to understand multi-objective. They use some of this. This is why I have to cover this. It's not because all of a sudden I fell in love with convex. I need this to move on, to do multi-objective. Okay, so a convex cone is the set that contains all the combinations of points in the set. All right. We kind of spoke a little bit about things like this. What happens here when he uses the term hyperplane? I guess you've done it in 3D calculus. What you have is the normal to the plane, and you have the normal to the plane, then you can get, I guess, a position vector here, B, X transpose minus B equals 0. Okay. So half space, if you stay only above it, okay, there's nothing new here. Euclidean, we spoke about this before. I hope you probably have seen this somewhere where you're talking about P, which is positive definite, and you have eigenvalues and eigenvectors that are reflected in the major and minor axis here, and this generates a an ellipsoid, multiple dimensions. Okay. And it gets, and there's more and more and more, and again, these are really simple definitions so that we can get to the action with multi-objective. Okay, so what a norm? There's a lot more that you can say, but we have the x equals 0 for the norm equals 0. You have the scalar property, and you have the triangular inequality, and you satisfy all of these, and you can get it. Okay, let's move on. Polyhedra. What is important, and the reason I went through these notes is the notations, okay? So what do they mean by this? Okay? What do they mean by this? And I guess they show you below where they generate this, and I'm trying to see this. Okay, so you're supposed to stay within the space, and that's what they're trying to picture for you. And I guess these will be, the big question I have is whether we're talking about the columns or the rows. And I'm going to guess that we're talking about the rows. but I could be wrong. Anyway, the point is that A defines, notice that if you take a vector orthogonal to that, then you can be on the above or below. Anyway, what this is that you need to take from here is the fact that this is component-wise. Let me say this again. This is component-wise. So basically, you plug in an x, you multiply by a, you generate a vector, right? Generates a bunch of numbers, and every component of that number shall remain less or equal to b. Okay? That's the only thing you need to understand, what that means. And therefore, in this case, notice that the space P satisfies all the inequalities defined by the hyperplanes in the sense that they are, in some sense, they have the, okay, you see the norms. So the concept here is that all of those guys satisfy these, they are in the interior of P. They satisfy the inequalities. In this case, it will be 0, usually, they say that we said. Anyway, I'm not going to worry about this, except the only thing that you need to understand is what we mean by that is component-wise. Okay? I mean, these are sketches. We're not going. This is probably one of the reasons I don't like this book. Okay, positive semi-definite is just defined in terms of X, which is a positive semi-definite matrix, nothing new, and that is the X++, which is positive definite, in that your matrix X here has to have positive eigenvalues, doesn't allow any zeros. We talked about these things. Okay. I'm not going to repeat that. Okay, I think we talked about this too. So are we done? So we can go to the fun stuff? Okay. All right. Okay, one of the greatest things about the textbook is and this is something that I would strongly recommend, worth reading this book for, is that is how do you preserve convexity? Where is it? We already. So, okay. So, and by the way, this was a huge focus for Peter as well. We did not focus on that as much. So basically, we have 2 points that belong to a convex set. So we already have a convex set C, and you combine them this way, then you're obviously going to be inside the set. Right? That's the definition of convexity. So if you start from convex sets, right, you can build others. All right? You can do intersections. You can build affine functions like they showed you, perspective function, linear fractional functions that they show in the book. By the way, I have a question for you. If you have a function, how can you prove whether a function is convex? What do? Does anybody remember? Yeah, but how do you show that?
It should be continuous at all points.
You need to take the second derivative, the Hessian, and establish that it's positive, definite, all over the place, everywhere. Okay, so or is positive, the second derivative. If it's a simple function, just call the second derivative, make sure it's positive. Okay? I'm surprised this is missing from here. Okay, so yeah, you can apply the definitions as well. All right, so now let's get to the fun stuff. Why are we covering this? Okay, so if you can just read it. All right, I was just at a defense this morning that student was doing multi-objective optimization, and in fact, he was really moving among the slides. I don't know if student realized. I don't even know if anyway, they had proper training in convex optimization. So why is this very important? Okay. Well, okay, so what's important here and what is new is that we're talking about a vector objective. Okay. And vector objective starts with Rn. That is no surprise. That's what we've been working on. But it lands in Rq, and Q could be greater than 1. That is so useful in the sense that in all of your, remember there are a couple of things that drive the future for you, right? That just like your midterm. Large-scale problems. You don't have derivatives, how do you do for you do stochastic optimizations, global optimization, how do you prove that things are global? Another thing that drives the future is to have multiple objectives. Okay? By the way, objectives come very naturally. They come from your constrained optimization problem. Another way to look at it, when you do constraint optimization, is to look at the constraints as objectives. So that's why I wanted it here. I wanted to talk about it before we go into general constraint methods. So instead of just saying that my solution will be, let's say I'm minimizing, I'm minimizing one constraint, you can have multiple, and you insist on having a solution that makes sense in multiple constraints. This is very close to what all of you are doing, okay? I mean, all of the dissertations that I've seen, they don't study one thing. They study, in fact, I've seen people, some of the students reject a solution because one of the objectives does not make sense, right? So it makes sense to think about it. So that's the difference. This is what's new about X. And this looks like there's probably a mistype here where one of them should have been equality here. Otherwise, the Fi and the Hi look exactly the same. So I think they probably wanted one of them to be equalities and the other one will be inequalities. Then it's the standard form that we cover. Okay. Okay. So if you have with respect to K, so K, remember they're talking about cones. The idea of cones is what we said before. You have all these vectors and you're taking positive linear combinations of them, right? We just saw it. It came in the previous slide. That's the only reason we covered it. So you won't run away when you see a cone. Okay, so if it's a convex optimization, then we're talking about convex functions everywhere. Okay, so in this case, first of all, you're talking about a K-convex where you're performing the optimization over a convex set, and K-convex set, and all the functions involved are convex. In this case, notice that they are equalities, I guess the HIs, got replaced by a simple linear equality. Okay, so do you guys remember why convex functions are so good? Why do we care about them so much?
Only have one minimum.
It has one minimum, but yes, that's number one. People sell it for that. But strictly speaking, there's another thing that is extremely interesting, is that once you have 2 points, your function is going to be below that. So you can always improve, right? You can just get the lowest points and go below it. So you got a lot of information if something is convex. I mean, yeah. All right. So let's move on. Okay. So, okay. So if you have 2 objectives, they're not showing it very well over here. Let's say one objective is along the x-axis and another one is along the y-axis, right? And you're trying to minimize both of them, right? And if you're trying to minimize both of them, that little corner is the best. It's 0 for both. Let's say, let's say the feasible set is what's drawn here as O. Notice that all the points inside the big O are feasible. Therefore, you want to go as further down. Notice, we're doing multiple objectives. That means that in this case, you're trying to minimize both. So you're trying to go as further down on the x-axis as you can, on the y-axis, as much as possible on the left for the x-axis as well. So definitely that point is the best, in that it achieves, in this case, let's say 0 for both. Okay? If it's not 0, it will still be the best because of the shape of the graph. Okay? Okay, that's why I'm putting my cursor on top of it. It achieves the lowest in both this axis and that axis. Now, in general, though, that's not going to happen. Okay? This is almost always trivial and completely non-interesting, right? all of the what you get in the most general case is this concept of Pareto optimality, which is it basically says that you're basically lying. First of all, you lie on the boundary, okay, and no other point can do better than you unless it sacrifices one of the objectives. Okay? Let me say this and say it again. Okay? And then I'll explain the graph. No other point from the solution will do better than you unless they sacrifice something from one of the objectives. So let's pick up this core point over there, which is the stupidest point of. It is the worst. That point is completely non-interesting because I can beat it with every point inside the O that is drawn over here. For example, if that point was interesting, let me look at it. Then the point that I left my cursor pointing at the new point, the new one is better than the other one because it's lower and also to the left. Okay? So it achieves a better result in both objectives. It is better because it's lower, and it's also better because it's left. So it beats that upper point in both objectives. So that's the definition of the Pareto optima. If you draw a little right angle of the shape shown, and this right angle goes to the left or goes down, and you trace it along the boundary, then the points that have absolutely nobody to their left, or they don't see anything inside here, think of this as a net. If there's absolutely nothing in this in this thing that I'm sliding up and down, then that point is Pareto optimal. That's a geometric definition. So so basically what I'm saying is that the graph that I'm tracing with my cursor up to there, and then it picks up again there, a little bit, not that point, but a little bit to the right, is the entire family of solutions that define Pareto optimal points. Okay? So I guess this is going to come up and I'm going to repeat it, but let's talk about it more and more. Okay? Let's keep talking until it becomes second nature, what's going on. So what's happening is that this is impossible. Usually you don't get one point that beats everybody else. In fact, let me pick an example from, for example, that's to give you a video compression that is used on your iPhone. The way they do it, every definition, about every 10 years, they redefine the video compression standards by essentially they want to keep exactly the same image quality, but cut the amount of bandwidth by 50%. That's one way to do it. But they're only looking at one point. My lab and a lot of our research, we look at solutions that go across edges. So in that case, you will say you can beat existing standards by basically finding points that are Pareto optimal, that are a better point where you are. Never mind, that example didn't. I think like maybe one person in here understands it. Let's pick something else. Let's pick minimizing energy, maximizing performance. I like it. Why? Because they're against each other, right? The more energy you put in, you expect a larger performance, right? So you're giving that constraint in your dissertation. Give me a solution that minimizes energy but maximizes performance, right? Very tough, right? They're against each other, right? If you give me a lot of energy, I can run supercomputers and give great performance, okay? If you give me very little energy, then I'll run it on the iPhone, and that's all I can get. So what's happening is that, let's say, where do you want to put the energy? Let's say the energy is along the x-axis. Let's say performance is along the y-axis. Okay? So let's say minus performance is along the y-axis. So the lowest you are, the lowest you are, the more performance you get. Okay? So this is a point of very low performance, but it's a point of also very low energy. You see how it works? So now, as you give me more and more energy, I can get more and more performance. That's the idea in multi-objective optimization. You sacrifice one, you get the other. Okay? It's a foundation of, oh boy, a PhD dissertation this morning, which was not my PhD, and a couple of my PhDs. We all start this way, and you might be starting that way without realizing it. I think you are all starting this way. How many of you think you have only one objective? Nobody? Is this a biased answer? You're trying to make me happy? I think you all have multiple objectives. Maybe they didn't give them to you that way. Okay? Okay, let's move. So, multi-criterion optimization. Okay? So now let's get a little bit more formal about this. Everything I said is in the previous graph, but now we're going to put a little bit more mathematics. By the way, the focus of my lecture is not the convexes. This is the focus, okay? I think you're going to get it because it's a very simple idea. So notice that I have Q objectives, okay? And they are in R plus. That means that, remember what we said before about cones, positive combinations, right? Q different objectives. And we all want them to be small, all of them. So my performance had a negative sign in front of it because, we wanted to minimize, right? So we will call it, notice that if you want to be feasible, optimality here means that it's very hard, right? You basically would like to have every single component, you have Q of them, to remain lower. So if I'm going to have, let's say I have 3 components, I plug in 3 functions, I get 3 values, and all of those values, one by one, are less than what I will get at any other point. Okay? If you can define your problem this way, then you have one possible solution. Everything we know generalizes. You don't have to look at Pareto. You don't have to look at surfaces. But chances are this is not going to be possible because you're interested in things that fight each other, performance versus energy. Okay? They push against each other. It's kind of like constraint optimization where they push against boundaries. Now, if that's what you have, yes.
What's that symbol?
As I said, this means component-wise. That means it's a vector. You're comparing 2 vectors, and every vector component has to be less than or equal. So it's not really new. We've been using it,
Yeah.
but they use this because they're engineers like us. Mathematicians don't care. They just throw it at you, right? Engineers are being cute. Because I'm an engineer too, but sometimes I wear my mathematician hat and make fun. I have multiple personality issues. Sometimes one part of me fights with another one. So. Okay, so let's have fun. All right, so now if it's Pareto though, it's a little bit different because if your Y is feasible, basically, first of all, let's go back here. The objectives are not competing. Okay, they don't fight against each other in this case. So you have this solution. Now, if you have a Pareto problem, I'm not sure if we can see this here. Then it stays to the left. It basically there's a trade-off between objectives, and therefore, basically, you have exactly the same. The only way to achieve the same performance is to be on that same point. So let me see if I can apply it to the graphics over there. Okay. In other words, if another point is equal, or if another x is above you, sorry. it's kind of a way of thinking about it negatively, and I'm not sure if I can even simplify it. But if there is a if y beats at every component, then it achieves the same value as the Pareto optimal value. It's kind of backwards thinking. Let's see it here, okay? What it really says is that you cannot find another point on the lower left unless it's optimal. So if you're picking up a y, then it's mathematics. It's giving you things backwards. If you can find another y, then that y has to be on this boundary. Never mind. I think the picture is more. All right. So let's look at one of our problems here. By the way, it's amazing because this regularized least squares is exactly a special case of the lasso that I gave you the elastic nets that I lectured on Wednesday of last week. Why is this? Does anybody know why this is interesting? By the way, I also put the lasso paper and the elastic nets online. So you can download the paper from Stanford if you want, and the software, how to write it. Why is this interesting as opposed to, let's say, just regular least squares? Do you remember last time? Why would you want to minimize both? The way to think about this problem, why it's interesting, is that, okay, so you're very used to this one, right? You're very used to least squares problems. Why would you also want to minimize the x? Because least squares problems tend to use all the x's, okay? But sometimes, so if your matrix is very large, they will end up using all of the columns or rows that you provide. However, most of the cases, you're very interested in fact, this morning was exactly this story. You're only interested in solutions that don't necessarily grab all the rows, or all the columns, okay? You're interested in a solution that the idea there is that if a value is close to 0, then you want it to come out to be 0. Notice that they showed you with cross-validation in the results that I showed on Wednesday that this is a better way of doing it because it's a bias variance option, and then basically they can actually show that if you follow what I was showing you with lasso and elastic nets, you are actually getting a far better fit as well in the least square sense when you consider the fact that you're doing cross-validation and machine learning. In other words, that is a far better approach than just least squares, okay? And I'll let you go over it if you want to. The paper is online. So there are wonderful reasons for which you'll be interested in minimizing both of them, right? Okay, so in this case, obviously the best point will be the one closest to this, right, lower left. But you need to apply the similar idea. Remember, I'm going to look to my left and also look down, and this point is far better than everything on that appears above it, right? Why is it better than all the points here? Because if you grab, I wish I had it, but if I grab the line and drop it down, you'll see that those points will be to the right of that little solid point over there. So this point killed everything above it. That's what happened there. And this point here also killed everything to its right. So basically, the only solutions that are really interesting are between those 2 points. Okay. By the way, guys, I'm sorry, I hate to say this, but all of you have least squares problems, and all of you at different stages might have this. Okay. You plug in the least squares and you get garbage, right? Okay, that's fine. I mean, everybody else gets garbage. The point is, can you bring a new idea, right? Can you say something new, right? And if you can say something new, we'll be very, very happy with your thesis or dissertation. You don't have to solve it, okay? But the most interesting problems are not going to be solved in your dissertations. But you have something new to say. And the multi-objective gives you that. Okay? You want to, by the way, and as I said, like most of you, almost all of you have this. And it would be nice to be able to say something completely original through this Pareto France. Okay. I fell in love with this, but trust me, I thought this looks weird. This is something I should be studying, and we've been studying it. And pretty much everything we do now we look at everything with multiple objectives. Let me give you one perspective. Does anybody know about receiver operating characteristics? ROC curves from radar, detection theory? Never mind. Don't worry about it. Okay. Multi-objective optimization can generalize a lot of things, including those.
Could I use the second term as like a distance measure?
Can I use the second term, this one?
Yeah, so if I set that as I'm looking for an optimal point about a certain location.
Oh yeah, you could. In fact, that's what we do. We have like a family. You know what we're doing? By the way, let me tell you another new frontier that all of the professors, at least the 12 professors in computer engineering, are totally interested in. By the way, I include Chalk in there with 0.25 computer engineering. Big data, right? Big data is like what Google is doing right now, right? It got gazillions amount of data available online. I just found out, by the way, that the paper I gave you and the method I gave you, that guy has like a special position on Google, like he's the head of their statistics department. So the stuff that I was talking about, they're using it, maybe. Notice that in Google, when you type a search, results come within seconds, right? So they're solving problems, optimization problems, on the fly, right in front of you, okay? So that's a new trend, believe it or not, for all of us. They're trying to take that to all problems that involve any amounts of data. In this multi-objective sense, I would be very interested. Notice that you pre-compute the Pareto France, and you can throw away all of this, right? So then the search, all it has to do is pull out some number I don't care. So here is an application, if you want it, if you're doing machine learning. But if you're not doing machine learning, you're doing regular least squares, you got to walk between those two. I would be totally interested. Notice that this solution here has the least squares answer, and this solution over here has, this point over here has the least squares answer, right? Because he's plotting F1 there, right? That one minimizes least squares. And this one has a higher mean square error, but it minimizes the x. So it would be fascinating to study the solutions between those two. It would be fascinating to study this point. Okay? All right, hopefully you use it. All right. Boy, I don't know much about portfolio optimization. Maybe I shouldn't even do this. So I guess I'll skip this one. Even though I'm convinced it's extremely important. Does anybody have a portfolio optimization? I know I studied it in a couple of projects. I've seen it in many papers, but I'm sorry I didn't prepare to give a 10-second presentation of it. So I'm going to skip it. You have to restudy things. All right. This is what happened this morning with the beautiful dissertation. Okay, multi-objective optimization. The student ended up doing what is called scalarization. Okay, and it's basically, let's go very slowly. It's a very simple idea, and all of you need to understand it. Okay, because it connects like 3 different things. Okay, so what is happening here is that in general, it would be impossible to evaluate the boundary, right? If you have the boundary, then, in fact, this is an assignment that you might get. Let me ask you a question. If I get you a bunch of points, can you generate this set? How would you do it? Huh? Taylor? No, don't take it. How would you evaluate the boundary? But this is an assignment that you might get, so let's pay attention to this problem. How can you get the boundary if I give you a collection of points? Collection of points, finite. All you have to do is go through a double for loop. Okay? Double for loop. Okay? Where you pick every point, you correct, and you compare it against all the other points. And you look, is there anybody to my left and lower, right? So you basically apply this definition to generate the Pareto optima for a finite. You basically take all the points and you say, okay, I have a counter. Every time I find, actually, you don't even need a counter. If I find any point to my lower left, this point is not Pareto optima. You understand the for loop? Just go through all of them and say, is there any point that is it is lower and to my left? In that case, reject that point, and you'll end up with the boundary. It's a very simple for loop. It's a very simple assignment that you might get. Okay, but in general, you don't have the luxury of having all those points. So what you want to do is, and this is exactly what they did here, is that they mapped it to regular constraint optimization in this case. So what they did is they put a lambda in front of it. And every time you change the lambda, you're basically generating a different point. Okay? So what the lambda is, you should look at it as I guess they're showing it to you right now. In order for you to minimize, so notice that if the lambda is pointing that way, and you will find this point. Why? Because you have orthogonality there, right? They're supposed to.
This is where convexity convex property comes into this. A hyperplane can only be tangent to the surface at one spot.
Okay, so that is a uniqueness theorem that you just call it. But the whole point is, actually, it's very simple. You can just put that slope in there and you'll find, I guess it's the same idea we're saying here. You can plug it in and you will find that there's only one point you're going to grab. I don't care if your point is not convex, though. If it's not convex, then you're going to grab more than one point, right? But I think the problem here is, I guess this lambda allows you to move around. That's all I'm going to say. All right. All right. So you minimize so here is the theorem right there. It's not you minimize the positive weighted sum. So this allows you, let's go back to the problem that we talked about, the least squares as well as minimizing the square. It gives you a wonderful framework to discuss all the solutions, right? What happens is that you can get all the points between here and here as a weighted sum of the two objectives. How many of you have weighted sums of two or more objectives? All of you, almost. Yes, you do, right? Yeah, all of you do that. Okay. Of course, in your case, if it's linear, don't worry, we're going to do the LP. But if it's not linear, then. But actually, if you do have weighted sums, so normally what happens? So basically, by moving around your lambdas, you're going to get a family of solutions, right? So going back to your PhD. If you have multiple objectives, it will be. In fact, I asked that question this morning. I should be with my mouth shut. Can you see that? Can you put the two objectives against each other and see what happens, right? Because it will be fascinating to find that. Basically, if you can find the right weights that way, that could change your whole dissertation. You understand? Normally, you plug them in, you get one answer, and that answer could be really bad. And then they tell, in fact, I remember when I was telling you when I came back from Asilomar and the professor said, I asked him, how did he set up the lambdas? And you know what his answer was? I call it the graduate student optimization. Well, it's okay for the student to stay up all night and run different lambdas. It would be nice if the professor had given a little bit more information so that the student knows what he's doing, or she. You know, so the story would have been what I wanted to tell the student if I had him is, this is what you're doing. You're trying to move between. You understand? You're not just plugging lambdas away. You're finding points on that surface. That's what I wanted the student to know. Okay?
Change the lambda.
You change the lambda, you get a different point. Yeah. And it will be fascinating to get those points. I mean, all of them will be very, very interesting. Okay. In fact, if you look at I posted the Stanford notes from machine learning. That's exactly what they do. They move the lambda and they show you that, hey, my coefficients remain steady.
Another is Lagrangian multiplier.
No, in this case, they call it, look, we call it the just weighted, positive weighted sum. So you basically define weights. Don't look at it as Lagrangian. But yes, there is a connection to Lagrange multiplier. Because if this was a constraint optimization, right, you could put constraints in here. Remember that we did with the lambdas, and they have to be positive for the inequalities, or we have it there in the interior, and all those KK2 rules where they play with the lambdas. We were very specific about those. They are not the same as those, as the ones we're showing today, but there are wonderful connections, right? The problem is that in most textbooks, they're doing multi-objective optimization, yet they are treating it as constraint, which is not true. In many, many textbooks, they're doing multi-objective, and they ask you to find regularization parameters and all that. They're really doing multi-objective, and yet they're saying this is the same as constraint optimization. It's not. Okay? And you guys know the answer. You've got it in your book. When are they the same? Right? There are constraints. Those Lagrange multipliers have optimal values. You don't change them. Right? Remember, they solve a problem. You find the lambda that are optimal. So I have no idea what that student who was staying up all night was he trying to do. Find the optimal values from the constraint problem, or was he doing a multi-objective where he was moving around the front? I have no idea. Tell me. Yes. Actually, thinking about it, I don't even know. I don't remember it, but I think he was doing. I think they were doing constraint, but they were using this formulation, which was completely wrong. Oh, it's also in the books on video compression, on the papers that they're confused about constraint optimization. They confuse it with multi-objective. Okay. Any more questions on this? Remember, so the answer about the equivalency is in your notes, right? KKT, optimal lambda, right? So it's not the same. When you're changing lambdas, it's not the same. Yet, and I have to be careful about it, there is a theory, which we might cover, about using these lambdas as weighted. That's different, though. By the way, let me tell you something else. Every time we tested those theories, we found out that they were cheating. In other words, the lambdas were never optimal, at least for real problems. For simulations, everything kind of worked. Yes?
But you said there's a connection for Lagrangian multiplier here?
Well, when we covered the theory for Lagrangian multiplier, we found lambda optimal. It didn't give you a family of solutions. It gave you one, right? It says it has to satisfy. At this point, the lambda star, have all these equations where you take the gradients of the constraints, right? And the gradient of your function, and they are totally aligned, and they don't have any other solution. Remember those proofs? Because they had to be on the same side, otherwise that's a specific value. Not, do you understand? Okay. This one is a family of answers.
We have zero vector.
Zero vector.
We have zero vector in that top equation.
You wouldn't have zero vector. There's nothing to do there.
F0
F0.
on the left-hand side.
Oh, okay. Yeah, that's because it's a.
That's a vector.
That's a vector function.
How did they?
This is a product between two vectors.
The question I've got is how did they find the vector function 0? The F0.
Oh no. That's how you start. Somebody gives you the F0. In your case, if you are doing least squares, I guess if you look at the lasso that I gave you, the elastic nets, they're actually looking at 3. And they do make the connection in your notes about constraint optimization, and they show it to you in that paper. They basically have a variable threshold in there. So there are connections. You just have to be careful how you state them. So what's going on is that okay, in least squares, in the paper that I gave you, they have 3 norms. Okay, the sum of absolute values of the coefficients, the sum of the squares of the coefficients, the x's, and the least squares problem that you guys are working on. It's actually 3 different objectives that are being at the same time being optimized. And then they vary the lambda because they're really looking at this. And they also show you the constraint optimization problem, which I'm assuming is rigorously done since they're in the math department. And what you will notice in that paper is that the constraint optimization has a variable threshold, which they don't specify. All right, never mind. All right. Is this fun or what? Okay, so I guess that's all I had. So are there any questions before I go into a little demo of math objective? Oh boy. All right. I'm not worried about the risk trade-off because I don't think anybody cares other than. All right. And I guess I'm going to stop there. I'm going to pause the lecture. Pause. And what I'm going to do is find out what I put online. Okay. So I put 2 new stuff online that I hadn't shown you. The first one is probably an updated version of the MATLAB help file. It looks very similar to yours. And in this case, it's slightly more sophisticated in the sense that they do have this concept. Notice that, look at this, that we spoke about this. Look at this. This is what happens. They vary the lambda. See that? Just like you had. And they keep track of the coefficients. One of them remains at 0. Why is that? Because it minimizes the 2 norms. The other one, notice how they change the lambda and they go, all of a sudden they pick up a, so they start, let's see, if the lambda is very large, they are over here on the left, and everything starts with all zeros, right? When the lambda is extremely, let's go back and see the definition. Sorry. So let's look at the definition to figure out what happens why that happens for very large lambda. I think they have it. We have it right here. Okay. So this is remember this is the simple version of the lasso, right? Where this is the least squares problem, right? The first term. And the second one simply adds up the absolute values of the coefficients, right? And the more sophisticated one, the one with what is called elastic nets, which generalizes the other one, has 2 norms, right? It has the least squares on the coefficients like we studied before, the vita square, and it also has this vita, the sum of absolute values. So if you plug in alpha equals 1, the quadratic term drops off, and you get basically the sum of absolute values of vita 1, which is the general lasso, right? On the other hand, if you plug in like alpha equals 0, then it goes to the multi-objective optimization problem that we discussed today. And the lambda plays the same role, right? The lambda allows you to balance between those two. So let's look at it together. If you pick up a very, very large lambda, then these norms become very important. So they're studying the regular lasso problem. So what happens is lambda goes to infinity, all of the betas are going to go to 0, right? That's exactly what we observed. When you pick up, on the other hand, if you pick in lambda equals 0, then you're going to get the regular least square solution. So by varying the lambda, you can study the problems, right, the answers, and you can decide if some of them are better than others. I really hope it works for you. That's all I want to say. If any of you are using this, I hope it works. Because the only thing I can tell you is that it's state of the art, so you might have, you make your advisors very happy if you start using this stuff. Hopefully yourselves too. Okay, so let's go back here. So sure enough, if I drag the lambda, in this case 10 to the first only 10, so if I plug in, I guess that will be my infinite lambda, it grabs all three of them to 0, right? And then I bring it down. So notice that in this case over here that they're tracing, this is like my least squares, right? Because your lambda is going down to 0 to the right. By picking different lambdas, you're basically cutting off your graph at different points, and you pick up the solutions as you go along. Okay? All right. And this is the least square solution for comparison. Notice that the least squares in MATLAB, this is not, they say something about that. It's not exactly, but so this is y times r hat equals x, and they use the backslash. The backslash gives the least squares algorithm. And they evaluate the residual. And then they do the same thing with cross-validation. Basically, does anybody know what we mean by cross-validation? This is the CV. Does anybody know what that is? Do you know anything about machine learning, pattern recognition? No. Okay. All right. So again, if you're going to get into this, okay, it's a very simple idea. Let me start with, it's a relative that is very easy to explain. If you have an incredibly small number of cases, very small number of data points, the first thing we apply is what is called leave one out. Leave one out means that, let's say I have 100 points. I guess I'm getting reported. I go through all of them, 100 points, but I train on the 99. In other words, I run my least squares on the remaining 99 points, and I do it 100 times, and then I test my fit, right, if my solution works on the last one. Basically, every time you do least squares, you generate a fit, right, and you can test it on a new point. So the cross-validation of 10 does the same thing, but tenfold. It's tenfold cross-validation. Instead of cutting it in leave one out, which means that every single sample gets left out and you train on the other one so you can see the variation, you do it by cutting it in 10 pieces. And you run 10 times. So it's much more manageable instead of doing, you know, if you have a very large number of points, leaving each one out, it could be daunting, right? You understand? You generate least squares and then you plot it, right? See how it fits. So in CV, it's done for you with the CV10. It cuts the data set into 10 pieces. It trains on 9/10, tests on the other one, the other 10th of the data. And all of that is done for you. And I guess the point of this is that they get to see the variation there. It's very fast. I mean, look at it. It's interesting to see all these variations. Again, I don't know if it's going to work for your problem, but it gives you something else to play with. So now you notice how the fourth coefficient that will be playing a big role in the least square solution, obviously non-zero, is completely wiped out if you are for large enough lambda. And I guess the point of this example is that they plugged in zeros. Let's see. Do they have the R? Notice that this is the ground truth. In their simulation, on purpose, they put 3 zeros. You see those? They put 3 zeros. And the question is, can you pick those 3? So the real answers, if we are on the same problem still, are going to be 2 and 3. Maybe -3. There's a -3 somewhere there. Yeah, -3. There it is. You see that? 2 and -3. 2, -3. The other one is 0. Even for any non-zero lambda, I picked it up over here. Okay. I think we're doing another simulation here, or aren't we? No, it's the same one. Yeah, it's the same one. -3 is here. Here is a 2. And these basically, they need to go to 0. 1, 2, 3. Okay? This is the mean square error. With varying difference of. I'm not sure what the colors are. I'm sorry, I haven't.
The colors are probably the different variables in the solution.
No, but they're plugging mean square error. I'm not sure. Minus the.
Well, it should be the mean square error fitting each one of those variables, 5 variables.
Actually, they are doing degrees of freedom. They have the different number of variables that they are using. One, so the different graphs come from the number of coefficients that they're plugging in. Okay, thank you. Yeah, the number of coefficients that they're plugging in, right?
Yeah.
And it's very interesting because okay, so if they plug in 4,
No, that's variable number 4.
variable number 4, no, it's df. It must be different plots. Degrees of freedom. I think it's the number of variables that they plug in. That's my guess, but you wouldn't know until you play. Anyway, so all right, so that's and they have a little bit of theory of how to pick. The last thing I want to talk about is the paper that I put online in case you guys want to get serious. Here is the paper. By the way, there are book on by these people, the machine learning book, which is extremely famous. You can actually download it from Stanford directly, it's PDF, that has this material. This is the paper that they try to describe if you really want to get serious, to see what they were doing. And I'm just going to go over it very quickly to show you. This is the naive case. This is the, sorry, I'm not going to add a sticky note. All right, these are the sums that we are talking about, V1, beta 2. Here is the formula in excess of a Lagrangian, where you have this beta, the different betas here. Again, you can look at it if you like. It's a multi-objective like the other guy did. Notice that it's equivalent to this constrained optimization problem. That's the connection that somebody was asking. What is the connection? There it is in this case. But notice that in order for them to make the connection, they have to pick some arbitrary value for t that they don't specify. So it's really not, I mean, it's not starting from the constrained optimization and going that way. I think it's probably better off to look at it as a multi-objective, okay? But if you would like to see it as a constraint, that's what you're doing. And but OLS stands for ordinary least squares. And they talk about the different types of solutions that they talk about connections to Bayesian, priors. Again, if you really want to get in, it actually didn't look like a very, I mean, it can be read. It's a really nice, it's very nicely written now. These algorithms, you can go and download them from Stanford. They are packages, which is basically well-tested algorithms. I don't know who wrote the MATLAB code, so I cannot guarantee it. All right, that's enough. All right, thank you, and I don't want to talk about this anymore.